The impact of climate change on the water quality of groundwater in Limbe-Cameroon. Abstract: a significant proportion of the population of Limbe, a coastal town in Cameroon, relies on groundwater, GW, to satisfy their drinking water needs. The coastal aquifer is threatened by pollution from seawater intrusion, and hence the aim of this study was to determine the suitability of the water. Physico-chemical analysis were carried out on samples collected from the study area, and the Revelle Index was calculated and used to determine the extent of pollution from seawater intrusion. The Water Quality Index, WQI, was calculated using values of the pH, bicarbonate, chloride, total dissolved solids and the electrical conductivity. The results showed that the sea level rise is projected to rise by 32 centimeters in 2050 and 82 centimeters in 2100 due to climate change from 2018, the base year. About 23% of the groundwater in the study area is currently slightly polluted by seawater intrusion. By 2050, this is projected to increase to 30.8% and to 42.31% in 2100 due to sea level rise resulting from climate change. About 34.4% of the groundwater in the study area is currently good for drinking, while 65.6% is either poor, very poor, or unsuitable for drinking. By 2050, it is projected that the proportion of the groundwater considered to be good for drinking will reduce to 26.92% and down to 17.86% in 2100. In order to reduce the intrusion of seawater into the aquifer, a halophyte plant like mangrove should be planted at the mouth of the main river in Limbe. Keywords: coastal aquifer, pollution, Revelle Index, salinity, sea level rise, seawater intrusion, water quality index. Introduction. In the last few decades, there has been a tremendous increase in the demand for fresh water in the world due to the rapid growth of the population and the accelerated pace of industrialization. 1. Limbe, a coastal town in Cameroon on the Atlantic Ocean, has a demand for domestic water supply that the water utility company cannot satisfy, and hence a significant proportion of the population relies on groundwater, GW, to meet their domestic water demands. Under natural conditions, coastal aquifers are recharged by rainfall, and the GW flows towards the ocean, preventing saltwater intrusion into the freshwater. The global mean sea level, GMSL, increased by an average rate of 1.8 mm/year during the 20th century too, and the IPCC reported with a high confidence that this rate has been increasing. 3. Reference 4 estimated that the GMSL increased by 3.1 mm/year from 1993 to 2003, but this change is not spatially uniform worldwide. Reference 5 estimated a GMSL rise of approximately 3.3 mm/year for the period 1992 to 2010. He 6 estimated, on the basis of data obtained from the tide gauge installed in Limbe, a rise in the mean sea level of the Atlantic Ocean in the lower part of the Gulf of Guinea of about 10 mm/year. One effect of such an increase is seawater intrusion into coastal aquifers. 7. Saltwater intrusion is a serious problem because about 80% of the world's population lives along the coast and utilize coastal aquifers for domestic water supply. In addition, overexploitation of coastal aquifers has resulted in falling groundwater levels, GWL. Sea level rise and falling GWL have resulted in increased pollution of GW due to seawater intrusion. This has caused wells previously used for domestic water supply to be abandoned. For example, in New Jersey, more than 120 wells were abandoned because of saltwater contamination. 8. In the study area, about 250 wells have been abandoned because the water has become salty. 6. Variations in the sea level and the associated wedge movement can influence the nearshore and or large-scale submarine discharge patterns and impact nutrient loading levels across the aquifer-ocean interface. 9. While anthropogenic activities, such as overpumping and felling of trees in urbanized coastal areas, are the major causes of saltwater intrusion, it is projected that increases in the sea level due to climate change, CC, would aggravate the problem. 9. Reference 10 modeled the impacts of climate change and changes in land use patterns on the salt distribution in a coastal aquifer and concluded that rising sea level could induce rapid progression of saltwater intrusion. Excessive groundwater withdrawals have been reported to result in changes in the physical, chemical, and microbiological water quality, drop in the water table level, reverse hydraulic gradient, and consequently water quality deterioration in coastal areas. 11. Poor water quality results in incidences of waterborne diseases and consequently reduces the life expectancy of the population. 12. Thus, concern for clean and safe drinking water and protection from contamination is justified because a large proportion of the population in the study area depends on groundwater for domestic purposes. Water quality evaluation is based on the physical, chemical, and biological parameters ascertaining the suitability for various uses such as domestic consumption, agricultural, recreational and industrial use. 13. The traditional assessment of water quality consists of comparing the point values of water quality parameters levels with their guideline or standard values based on allocated water use or uses. This type of assessment does not provide an overall assessment of water quality of a water body, which is important for managers and decision makers. To resolve this decision-making problem, several water quality indices have been developed to transform point value water quality parameters into integrated indicator values. Many studies have demonstrated the usefulness of assessing the water quality of GW using a water quality index, WQI. Examples are presented by 14, 15, 16, 17, 18, 19, 20, and 21. The aim of this study was to assess the suitability of the GW in Limbe for domestic use in a changing climate, specifically to determine the effect of climate change on the seawater intrusion in Limbe, evaluate the change in the extent of seawater intrusion into the aquifer due to climate change, determine the change in the proportion of the GW suitable for drinking due to climate change, and propose a solution to reduce the impact of seawater intrusion on the GW quality in the coastal aquifer. 2 Materials and methods. A. The study area. I. Location. Limbe is located along the coastal area of Physico Division, southwest region of Cameroon, Figure 1. The study area is located approximately between latitudes 3090 and 4005 N and longitudes 9029 and 9006 E. It is bounded in the east by Bimbia, in the north by Bonaticambo, in the south by the Atlantic Ocean, and in the west by Makundange. The population of Limbe is about 130,000 inhabitants spread over a surface area of 596 square kilometers 22. The town is characterized by a low-lying coastal plain, rising up to a chain of horseshoe-shaped hills towards the northeast and east, with the highest point at 362 m above sea level 23. Within the town, small rivers flow into larger drainage channels that converge into the main river, Engingal, that empties into the Atlantic Ocean, Figure 2. These rivers frequently overflow their banks in the rainy season, causing floods in the low-lying areas that are only 1 to 2 m above sea level 24. The hills that surround the town are made up of loose ferrolitic and volcanic soils that easily disintegrate when the water content is high. 25. 2. Climate. The climate of Limbe is the sub-equatorial type with 2 distinct seasons, a dry season of 2 months from December to January and a rainy season of 10 months from February to November, with a mean annual rainfall of 3,100 mm, plus or minus 1,100 standard deviation. 27. The monthly rainfall frequently exceeds 500 mm and sometimes is over 1,000 mm in June, July, and August. The mean annual temperature is about 26 degrees Celsius, while the relative humidity is generally above 85%. 28. 3. Geomorphology and Hydrogeology. The study area is made up of ridges, Alpha Club Hills, White Man Hills, Caterpillared Hills, Bend Hills, Tal Hills, Mile 2 Hills, Mabetanu Layout Hills, and deeply incised ravines with a W-E orientation at a high angle to the general N-E-S-W orientation of Mount Cameroon. 27. These ridges form part of the Limbe-Mabeta volcanic massif, made up of degraded and deeply weathered tertiary basaltic lava flows. 27. The elevations in the study area range from 0 to about 90 m above sea level, with slopes ranging from 0 degrees to 43 degrees, Figure 3. The main rock types within this area include basalts, Figure 4, bosonites, lahar deposits, and pyroclastic materials. 26. The hydrogeology is characterized by unfossiliferous sandstone and gravel, weathered from underlying Precambrian basement rock. 29. It consists of coastal plain sands, CPS, and recent sediments. The CPS aquifer is the most productive and exploited aquifer in Limbe. B. Data collection and analysis. Water samples were collected monthly between July 2017 and June 2018 from 30 hand-dug wells located along 3 transects as shown on Figure 1. The sample size was determined using the formulae presented in 1 and 2, 31. The electrical conductivity, EC, the pH, and the total dissolved solids, TDS, were measured in situ using a portable handheld, pH 0.286 in 1 monitor. Water samples for laboratory analysis were collected in clean 150 ml polyethylene bottles and preserved in ice chests for analyses of chloride and bicarbonate using standard methods. 32. The coordinates of the sampled wells were recorded using a global positioning system, GPS, and thereafter were plotted using ArcGIS software on the geomorphological map of Limbe. To get a comprehensive picture of the overall quality of groundwater, the Water Quality Index, WQI, was used. WQI is defined as a rating reflecting the composite influence of different water quality parameters on the overall quality of water. He 33 proposed the following: 3. For calculating the Revelle Index, RI, which is used to assess groundwater pollution from seawater. According to 33, when RI 0.5, this indicates there is no seawater intrusion. When RI is between 0.5 to 6.6, this indicates the GW is slightly affected, and when it's greater than 6.6 it indicates it's strongly affected. The drinking water quality was assessed using a Water Quality Index, WQI, and the 12 standard. The stages of calculating the WQI are as follows. Q. 4. Where Qn equals quality rating for the nth water quality parameter. N equals the water quality parameter and quality rating or sub-index, Qn, corresponding to nth parameter, i.e. a number reflecting the relative value of this parameter with respect to its standard, maximum permissible value. Vn equals estimated value of the nth parameter at a given the sampling point. Sn equals standard permissible value of the nth parameter. Vio equals ideal value of nth parameter in pure water, i.e. 0 for all other parameters except pH and dissolved oxygen, 7.0 and 14.6 mg/L respectively. The unit weight of the nth parameter, Wn, was calculated by a value inversely proportional to the recommended standard value, Sn, of the corresponding parameter. Wn equals K. 5. The coordinates of each sample were determined using a Garmin GPSMAP 78S. The values of the Revelle Index and the Water Quality Index were then exported to the ArcGIS 6.0 software and used to generate maps of their spatial distribution over the study area. The areas referring to each water quality class and the Revelle Index were circumscribed on the map using ArcGIS 6.0. They were automatically generated with the software surface function. Finally, slicing options were applied using these ranges of values with 5 groups of water quality classes to generate a spatial distribution of water quality map 34. The statistical analysis of the examined groundwater parameters was computed using Stata software version 6.0. See effect of CC on seawater intrusion. The effect of CC on seawater intrusion in the study area was determined using the estimation of the SLR, the determination of the retreat in the shoreline, the hydraulic head of the coastal aquifer due to CC, and the velocity of the GW. Reference 6 showed that there was a correlation between sea level and the temperature of ocean surface waters at Limbe in Cameroon. This study noted the increase in sea level at the Limbe coasts of 10 mm/year and a retreat in the shoreline of 32 cm/year. This recession will leave a space favorable to saline intrusion, the consequence of which will be the advancement of the salt water front. The projection of the sea level rise for 2050 and 2100 were obtained by using the 7 and 8, respectively. SLR 7. SLR 2100 equals annual rate of SLRx, 2100 to 2018. 8. The projected retreat or recession in the shoreline in 2050 and 2100 were obtained using 9 and 10, respectively. Retreat in the shoreline in 2050 equals a 9. Retreat in the shoreline in 2100 equals annual retreat in the shoreline rate x, 2100 to 2018. 10. The velocity of flow of the GW in 2018 was obtained using Darcy's formula in 11. V equals K. 11. Where V equals velocity of flow of the GW, cm/s. K equals soil permeability, cm/s. I equals hydraulic gradient, ratio. The soil permeability was obtained using the Porchet method, figure 6. For this, a cylindrical hole was dug with an auger 10 cm in diameter and 50 cm deep. After filling the hole with water, the height of the water h1 was noted at time t1 and later h2 at time t2. Figure 6. Measurement of the infiltration rate by the Porchet method. Source, 35. The permeability of the soil K was obtained from 12. K. 12. Where K equals soil permeability, cm/s. R equals radius of the hole, cm. H1 equals height of the water, cm, at time t1, s. H2 equals height of the water, cm, at time t2, s. In a free porous type aquifer, the dominant flows are horizontal, consequences of a weak hydraulic gradient in low-lying areas 36. The piezometric level is influenced by the geometry, the topography, the hydrodynamic properties of the soil and the operating conditions. From the base year of 2018, wells that had been affected by salt intrusion were retained because their hydraulic heads were greater than the other wells. The salty well, P3, with the highest hydraulic head and the well, P9, with the lowest hydraulic head were used for the estimation of the hydraulic gradient. The hydraulic gradient of the aquifer water was determined using 13. I equals dH/dl. 13. Where I equals hydraulic gradient, ratio. dH equals the difference in head compared to an upstream well and a downstream well, m. dl equals the distance between the two wells, m. The salt front was measured from the coastline with the distance measurement application in ArcGIS software. As the sea level rose, this front had to move from the highest hydraulic head to the lowest due to the increased hydraulic head in the wells in the critical zone. The simulation of 36 gives the hydraulic head in the coastal aquifer equal to half the rise in sea level during this period, and this was used in the study. The salt front during displacement affected new wells, P6, P7, P10, with concentrations equal to those of wells from the initial position of the salt front. These new concentrations were substituted with the old concentrations from where the Revelle indices for 2050 and 2100, only well P8 was affected and P10 excluded, were calculated according to the formulas of 14 and 15. RI 2050 equals 14. RI 2100 equals CL-2100 HCO3- plus CO32-. 15. For the projections with rising sea levels due to climate change, the hydraulic gradients for the years 2050 and 2100 were estimated based on the 16 and 17. The new velocity of the salt fronts for these respective years were obtained with the 18 and 19, and finally the projected displacement of the salty front were obtained with 20 and 21, respectively for 2050 and 2100. I 2050 equals DH 2050 DL. 16. Where I 2050 and I 2100 are the hydraulic gradients in 2050 and 2100 respectively. DH 2050 and DH 2100 are the difference in load compared to an upstream well and a downstream well in 2050 and 2100 respectively, m. DL equals the distance between the two wells, m. V 2050 and V 2100 are the velocities of GW in 2050 and 2100 respectively, cm/s. K is the soil permeability, cm/s. D 2050 and D 2100 are displacements of the salt front in 2050 and 2100 respectively, m. T50 equals 2050 to 2018 equals 32 years. T100 equals 2100 to 2050 equals 50 years. As the hydraulic gradient will change with the sea level, the impact will be on the concentration of chloride. Wqi for the years 2050 and 2100 were obtained with 22 and 23, respectively. Wqi 2050 and Wqi 2100 were imported to the software ArcGIS for digitizing maps. The areas occupied by the various water quality classes were obtained after circumscribing each color with the surface application of the software. 3 Results and discussion. A. Effect of CC on seawater intrusion in Limbe. Following the correlation between sea level and the temperature of ocean surface waters in Limbe, the rise was estimated to be of 10 mm/year and a receding shoreline of 32 cm/year in 2018. In 2050 the rise in sea level was estimated to be 32 cm compared to the reference year of 2018, while the coastline receded by 1.024 m. In 2100, the rise in sea level was determined to be 82 cm and will lead to the coastline receding by 2.624 m compared to the 2018 value. The salt front was determined with ArcGIS to be located at 779 m from the coastline in 2018. The hydraulic gradient was negative with a value of -0.405% in the area occupied by wells P1, P2, P3, P4, P5, and P9 as shown in Figure 7. This gradient was given with wells P3 and P9. The velocity of the GW in this critical area was 9.35 mm per day with an average permeability in the study area initially found of 2.308 m/day in 2018. It is projected that the velocities of the aquifer subsequent to sea level rise will be 9.75 mm per day and 10.60 mm per day respectively in 2050 and 2100. The salt fronts will be about 114 m in 2050 compared to the position in 2018, and 317 m in 2100 compared to 2050. Studies had revealed that the rate of recession of the coastline in Rio del Rey in the Bicarbonate Peninsula in Cameroon was 10 m/year 37. This is much higher than the rate of 32 cm/year determined in the study. It is also very different from the values found on the Togolese and Beninese coasts where the coastal drift is more pronounced on the coasts. Reference 38 found that the rate of recession of the coastline in Benin was about 12 m/year on a segment of coast of approximately 5 km for more than 10 years. In Togo, the consequence has been the relocation of the Akrikotano motorway twice, loss of land and displacement of local populations living exclusively on fishing. Elsewhere, even if the available data are less alarming, they are no less worrying. In Ivory Coast for example, the recession of the coastline vary on average from 1 to 3 meters per year 39. B. Extent of seawater intrusion in the coastal aquifer in a changing climate. In the study area, Ri varied from 0.126 to 1.551 as shown in Table 2. According to Revelle, 1941, 33, this suggests that some areas in the study area have not been affected, Ri less than 0.5, while others have been slightly affected, Ri is between 0.5 and 6.6. The relationship between the ratios of Cl-HCO3- plus CO32- indicates a strong positive linear relation with Cl concentrations, R equals 0.94, P 0.01. This linear relationship indicates the mixing of saline water and fresh groundwater. 15. Figure 8 shows the extent of the groundwater salinization in the study area. From Table 3, about 77% of the groundwater in the study area was unaffected by seawater intrusion, while 23% of the aquifer was slightly affected by pollution from seawater in 2018. The hotspots include locations of wells P1, P2, P3, P4, and P5. Thus, efforts should be made to reduce the pollution of groundwater due to sea level rise in the area. Table 2. Revelle Index of GW in the study area. Transects. Wells. Coordinates, meters. Revelle Index. With the projected sea level rise, SLR, of 32 cm in 2050 and 82 cm in 2100 due to climate change from the 2018 the base year, the hydraulic head will be increased in the critical wells by 0.16 m in 2050 by of 0.492 m in 2100 based on simulations by 36. A negative hydraulic gradient will be noted and will lead to the change in the RI. Figures 9 and 10 show the spatial variations of seawater intrusion into groundwater in 2050 and 2100 respectively as influenced by projected sea level rise. The area covered by various RI were calculated from the RI maps and given in Table 3. The area slightly affected will increase from 55.36 Ha in 2018 to 74.32 Ha in 2050 leading to an increment of 7.8% of the total area lightly affected. The increment will be 11.51% by the year 2100. See extent of the GW suitable for drinking. The suitability of groundwater for drinking purposes in the study area was determined using WHO, 2006, 12 guidelines. The computed Wqi ranged from 28 to 115 as indicated in Table 4. The area covered by different water quality classes were calculated from the Wqi maps, Figure 11, 12, and 13 respectively for 2018, 2050 and 2100, and are presented in Table 5. About 34.4% of the GW is currently considered to be good for drinking while 65.6% is either poor, very poor, or unsuitable for drinking. As the years go by, based on projected sea level rise due to climate change, the amount of seawater intrusion is set to increase if there are no mitigating measures. The proportion of GW considered to be of good quality is therefore projected to reduce as more GW becomes polluted by seawater. From Table 5, in 2050, the proportion of the groundwater considered to be good for drinking will reduce to 26.92% and down to 17.86% in 2010. Hotspots that require attention are wells P2, P3, P4, and P5, all along Transect 1, which is closest to the sea. The EC, pH, TDS, Cl and HCO3 all contributed to the Wqi values. However, values of chloride and electrical conductivity were the main parameters responsible for the high values of Wqi. In some locations, the TDS also significantly increased the Wqi. D measures to reduce seawater intrusion. About 23% of the aquifer of the study area is affected by seawater intrusion, rendering the water non-potable. In order to reduce the intrusion of ocean water, there are two possibilities: construction of dikes or barriers, and planting a halophyte plant. Anti-salt barriers or dikes can be used to combat saline intrusion 40. However, they are limited in that they are effective only in controlling surface seawater flow, but they do not prevent the intrusion of underground seawater 41. A more effective solution is the planting of halophyte plants like mangrove trees of the Rhizophyraceae family. They should be planted on both sides of the mouth of the river Enjingal over a distance of 500 m. Mangrove trees stabilize the coastline and serve as a barrier against erosion due to swell by reducing the energy of the waves and by modifying the hydrocirculations 42. Mangrove trees have a root system that filters water, and can thus exclude up to 90% of salts from interstitial waters thanks to glands located in their leaves 43. Mangrove trees planted a short distance offshore control high-energy waves which erode the coastline and prevent the meeting of coastal marine waters and fresh waters. In addition, the complex geochemical reactions taking place in the sediment around the trees can immobilize toxic metals and consequently purify coastal waters. Furthermore, mangrove trees serve as a natural barrier against the gradual rise in mean sea level and saline intrusion into aquifers and arable land. They also have a significant refuge value and hence they enhance aquatic biodiversity. 4 conclusions. Based on the methodology used in the study and the results obtained, it can be concluded that 1. The sea level rise is projected to rise in Limbe by 32 cm in 2050 and 82 cm in 2100, from the base year of 2018, due to climate change. 2. About 23% of the groundwater in study area is presently slightly polluted by seawater intrusion. By 2050, this is projected to increase to 30.8% and to 42.31% in 2100 due increased seawater intrusion resulting from sea level rise because of climate change. 3. About 34.4% of the groundwater in the study area is currently considered to be good for drinking, while 65.6% is either poor, very poor, or unsuitable for drinking. By 2050, the proportion of the groundwater considered to be good for drinking in Limbe will reduce to 26.92% and down to 17.86% in 2100. Hotspots that require urgent attention are locations of wells P2, P3, P4, and P5. 4. To minimize the impact of seawater intrusion on the quality of GW in the study area, a halophyte plant like mangrove should be planted at the mouth of River Enjingal, which is the main natural drain in the study area. Disclosure statement. No potential conflict of interest was reported by the authors. Acknowledgements. The authors are most grateful to the Water Utility Company in Limbe for their collaboration in the study. Special thanks to all those who participated in the collection of data, in the laboratory analyses, and to the population of the study area for their support.